Okay, so hello and welcome to our webinar, to our VicInAqua webinar. We are quite happy to have all of you here participating in this quite nice experience. And today we want to talk about turning water and energy challenges into opportunities. And yeah, as announced, we specifically want to talk about our project, the VicInAqua project. So my name is Carsten Bolz from Steinbeis. We are one of the partners in the project, and I'm also quite happy to welcome our two speakers today, which are Professor Jan Hoinkes and Julian Mamo, and I just want to give them the opportunity to introduce themselves.
Good morning, everybody. My name is Jan Hoinkes. I'm the coordinator of the VicInAqua project. From University Applied Sciences in Karlsruhe, and my expertise is basically on so I'm coming from the chemistry side, so environmental chemistry, thermodynamics, process engineering, in particular in water treatment and water reuse, combined with sensor and control systems. So I can pass the floor to Julian.
Good morning, everybody. I'm Julian Mamo. I work for Aquabiotech Group, which is a company based in Malta, on the island of Malta. And my expertise is environmental engineering. In this project, I'm working particularly on recirculating aquaculture systems. Thanks.
Okay, thank you. Before we jump into the webinar, I just want to shortly let you know that we also have other activities within the VicInAqua project. We have quite recently two large events that are coming up. The first one is the VicInAqua conference on the 21st of November at the Kenya Water and Sanitation Week in Nairobi. And the second one is the inauguration of our pilot in Kisumu on the 23rd of November. So we are quite happy that we are able to also have a physical inauguration of the pilot. Also, if you want to get involved, just check out our website. There you can join our stakeholder community, subscribe to our newsletter, or you can just follow us on LinkedIn, Twitter, and Facebook, or also you can just drop us a message. Okay, what is the agenda for today? First of all, we want to shortly talk about water and energy challenges, then come to the case of VicInAqua, where we then will get a project overview. We'll talk about the different technologies we use in the project, and please feel free to ask any question during the webinar. On the bottom right, you have a chat function, and there's a little question mark icon. Please use it, just click on it, and then you can ask a question, and we will feed your questions then into the questions and answers section, which will be at the end of the webinar. So first you can enjoy and listen to the presentation, and then we will discuss your questions. Yeah, so let's start. In recent years, water and energy challenges become increasingly important to industry regulators and users. However, these are also often associated with new business and innovation opportunities. But what are these global water and energy challenges? And here just to up some of the challenges. The first one related to water is the growing water demand and water scarcity. The demand is predicted to increase, and specifically here in our case, which is important, that the main part of this new demand is driven by agriculture. And the same elements of the agriculture sector is true for water pollution. Their industrial and the agricultural sector is the major source of water pollution. Also, there's a lot of freshwater ecosystems at risk at the moment, and that's also one of the challenges within our project, because we are addressing the Lake Victoria Basin. So this is kind of the starting point for the project, are these global challenges. Related to water, to energy, we also have some challenges there, which is related to affordable and modern energy supplies, which in some parts of the world is people are lacking access. And we have often unreliable energy supplies, which is also a hardship and economic burden for large portions of world's population. In addition to that, we have high impacts of the energy production on human health, but also on the environment. However, there's no silver bullet solution for these challenges. There's no one single fixed solution to any of these challenges, but we can start thinking about, okay, how can we solve those? And we can also make contributions to solve those with, like, I would say, small projects, small steps towards this goal. And therefore, VicInAqua was set up. It's a research project to develop and integrate new technologies, addressing both water and energy challenges, and also to draw key learnings on how such technologies can be made available in environments as such in Kenya, because the pilot will be, or we are building the pilot in Kenya, in Kisumu, to demonstrate that the technology works. And now I want to hand over to Professor Jan Honkes to talk more in detail about the use case of VicInAqua.
Yeah, thank you. I would like to give you a project overview. And so what is the VicInAqua rationale? So how is the situation on the Lake Victoria, which is one of the biggest sweetwater lakes on our planet? And it's a typical example like in other areas as well. So it's not only in Africa, it's in Asia and in other regions on our planet as well. So it's, as you could see, high population, rapid urbanization. This is a general problem everywhere. It's a high rate of poverty, poor sanitation system, and the growth of the fish processing industry hampered the fishing. So the yield of the fishing, so the fishing industry was on decline during the last years, and there's only few fish anymore due to this bad water situation in the lake. Wastewater discharge into the Lake Victoria gives over-fertilization, eutrophication it's called, in the water. It's also worldwide known. So growth of what you could see on at the bottom on this image, when I was first time coming to Victoria, I also noticed the lake was not blue, it was green instead, and this was due to the growth of water hyacinth, which covered a great part of the lake, and algae. This is also an indicator for eutrophication and over-fertilization. Overfishing already mentioned. So I met many people around who are now working as a taxi driver. They were previously fishermen, but due to the decrease in fish population in the lake, they cannot make their survival by fishing, and they're looking for other jobs. So this is very, very, very critical. And I also learned that the fish processing industry is also in decline. So they try to import fish from other countries in order to keep their production going, and because there's not enough fed from the lake. And of course, the lack of awareness on the impact and fisheries and wastewater discharge. So what is our vision in VicInAqua? It's the main purpose of this is so-called self-cleaning water filtration solution, a multi-purpose filter which is able to take care of sanitation and at the same time being able to feed water to the RAS, to the recirculation aquaculture system. And in addition, these are some more details to ensure a denitrification of these systems, but these are later on coming to more details. It's also capacity building, so the technological development demonstration in this critical and difficult environment at the Lake Victoria, to involve a network of already existing aquaculture activities at the Lake Victoria. It's more coming, and it's like a booming sector, and more people like to go into this. So to go into this network and to see how we can collaborate with others. And one of what we learned, what is important in this area around Lake Victoria, it's not so much in urban, it's called peri-urban. So this is more like the outskirts of the urban areas. This is a critical area, and we are addressing this. And later on, you can see that we set up our pilot in one of these peri-urban areas. It's shown later. And yeah, it should finally VicInAqua a solution as a tailor-made response to the needs of the population and industry as well. And of course, as you may know, the main challenge is always to keep the cost, to keep the system simple, and to keep the cost at an acceptable rate, so that later, this is the idea, this can be replicated and taking as an example for future business to set up more units like this and to run it as a good business, so that we can also create jobs in this area, what is lost in the fishing industry, to create more jobs in the aquaculture sector. So coming to the next slide, the consortium of our project consists of European partners. So we from Karlsruhe, we are the coordinator. Steinbeis, Carsten Bolz, they represent the management unit. So they support all kind of management and financial budgeting. And we have partners in Italy. They are more concerned with membrane, details coming later. New novel membrane development. We have Julian, who's online with us from AquaBiotech, aquaculture company. They are closely related to Oxygard. They're supplying the sensor and control system. We have a German company supplying the PV or improved PV systems. And of course, we have our very important, our African local partners in Uganda, Kenya, and Tanzania. These are the bordering states of the Lake Victoria, and we try to balance all this so that we are all around the Lake Victoria finally, and to disseminate and to show off our findings. And last but not least, not to miss this, very important, the Department of Agriculture and Livestock in Kisumu. This is the arrow at right up at the Lake Victoria. This is where we set up our pilot, where we would like to run the pilot. Details coming later, and they are taking care of all these managements around the pilot unit. So a very important partner as well. Okay, what are the main objectives? I quickly mentioned novel membranes for water treatment, for the wastewater treatment in membrane bioreactors. So gonna give you more details further on. Integrated renewable energies, this means photovoltaics and biogas. A robust and real-time sensor system for the water management supplied by our partner Oxygard. A environmental impact assessment. This is done by our African partners, and socio-economic studies, because they know the situation down there very well. Awareness raising, capacity building, workshops on the different technologies, knowledge transfer, very, very important. And finally, last but not least, gender equality, better integration of women. So in aquaculture, there are already many women hired, and we want to further expand this rate of women integrated. So, okay, just a quick look, a general look on the knowledge transfer. So basically, we can say that the technology or the novel technology from the European partners will be transferred to the the environment near the Victoria Lake. And of course, there should be feedback on socioeconomic aspects on different levels coming from our African partners, so that we can suit and adapt all of our, from the European perspective, that we get the feedback, what are the needs and the requirements in Africa. So this is just in general shown by this slide. And okay, the technologies. Okay, this is a very important slide, because this is giving you the overview on our technologies and the overall system, our holistic approach on this. As you can see on the right hand, the core is the RAS system, recirculating system, and the MBR is connected to this RAS system. And as already mentioned, as you could see left hand up, the MBR is meant as a multi-purpose filter, so that we are also able to feed treated wastewater, domestic wastewater, and industrial, from processing industry wastewater into the system in order to save water. And this water treated by the MBR from the system, the surplus water can be used for agriculture and irrigation. So in our later, we can show you the photo that we have prepared, a small field where we want to grow some vegetable and some other plants, and this will be irrigated by the water from the system. And the energy supplied is generated by PV and biogas. So it's very important to notice that the system is not completely autonomous. At the beginning, we were planning like 100% autonomy. However, we learned that this is not required. So we are providing a majority of the energy by PV by renewable energies. However, we also connect it to the grid. And very important in Africa is there are frequent power outages, and so to get these power outages by our system, this was the main concern of us. So that if we could not feed any oxygen to the fish or to the MBR, everything will be killed. And so we have to ensure a smooth operation of the system, and this is our main concern. And of course, left hand up, the online monitoring, which can be also remotely checked by people and on the ground and remotely controlled as well. So this is the basics of our system. Okay, membrane bioreactor is nowadays well known and widely applied in a variety of sectors. You probably know about this. What is an MBR bioreactor? So you probably know the sewage treat, the conventional sewage treatment plant, and the MBR is like a 3-in-1 system. So it combines a reaction tank, the activated sludge process, with a sedimentation. So by filtering, replacing sedimentation by filtering, and these membranes are able also to disinfect the water, because they will be retaining all germs, bacteria, and so on, that this water can be it's suited for irrigation or for a system like in the RAS. So the main characteristics of this is low footprint. It's very compact, very small, much smaller, since we do not need any sedimentation tank, and the water quality is outstanding, and so we do not need any if you want to be 100% sure, you could add some extra disinfection like UV and so on. It's basically a safe system, a safe barrier in order to reject germs, bacteria. And there were other on the right down. You could see other advantages. The mixed liquor suspended solid is much higher, so it's more efficient. The degradation process is more efficient, and so, as I said in summary, it's perfectly suited for water reuse. The other field where our Italian partners are working on, no details because it's too short and we have not much time. And just to give you the basic idea, we're starting with the commercial MBR membranes, polymer membranes basically. And what we try is to improve the so-called anti-fouling properties of this membrane. So fouling layer on membrane, this is the great concern and the major problem when in real application of the MBRs. And we try to cast a novel anti-fouling layer on top. It's cured by UV light. And so we have done a lot of work already in the lab, and this will be coming, and the pilot test will be tested in Africa as well. And this SEM down at the bottom shows you this is a nanostructured novel coating which shows antimicrobial properties, so repelling any fouling agents, and it's also a very smooth surface. And what we have shown already on small pilot that we can run a higher volume flow in general, so in long term. So what definitely will reduce the cost of the operating cost and the capital cost as well. So this slide shows you the two of our results. So with the model foulant humic acid, so on top you could see the commercial membrane and the PPM coated, showing a thinner coating, fouling coating on the membrane. So just one general image on this. And as you know, in these systems, the membrane will be submerged in the activated sludge tank and will be run by suction, left hand up. You could see suction pump, and this is also what we have set up in Kisumu in Kenya already, and so we are ready to go. We first want to start with the commercial membranes, and in a later phase we want to compare in the same tank the novel membranes with the commercial ones and hopefully see the benefit of this. As already mentioned, reduction of surface roughness, higher hydrophilicity and antimicrobial property. This is the characteristics of the novel membranes, of the novel coating. Okay, now I can pass the floor to Julian. We are now coming to the RAS system, and
yes.
which is set up and will be monitored by our partner from Malta. So, Julian.
Thank you. So the water from the MBR system, actually in the pilot, we're also including a UV system. So the permeate, the product water coming from the MBR, from the wastewater treatment system, is actually being passed through a UV before being coming into the aquaculture system. As regards the RAS system, the aim of this is to create a training facility, although the facility will be a facility which will be used as a hatchery. The aim is to have a system which will be used for training and development purposes. The capacity of the system is 25,000 fingerlings per month, which is not a huge system, but it's of a capacity which is suitable to show how things work, how the different systems work together. As such, so we have three systems. The first big system, which you could see in the picture above, is the broodstock and egg incubation system. Egg incubation is at the far end of the system. The aim here is to have broodstock also in RAS. Initially, we were thinking of having broodstock in ponds, but the idea was to have a completely closed system, have a system which is completely self-contained within the VicInAqua pilot. And the second system is the larvae system, and the third system is the nursery. As the RAS process goes, I'll explain a bit in the next slide. Basically, the water is continuously recirculated between the fish tanks, between the culture tanks, and the treatment system. So in this treatment system, there are a number of key processes. There's a solid separation process, a solid removal process, then there's a nitrifying bioreactor. Then we aerate the water before the water is returned back into the fish tanks. And typically, a system like this can be run with an exchange per day of 10 to 15%. The aim is to run with lower percentages than this, but generally we have to top up the system with between around 10% of new water into the system, which in the VicInAqua case is coming from the membrane bioreactor. And then water which we are removing from the RAS system is actually going back to the MBR where we'll be denitrifying. So the ammonia generated by the fish and is converted to nitrite and nitrate in the nitrifying bioreactor. The water, basically we have an accumulation of nitrate in the system. This water is also recirculated back into the wastewater treatment process to reduce to denitrify, okay, so to convert the nitrate into nitrogen. And the solids from the solid separation process are going into the biogas generation, into the anaerobic digester. The aim of all of this, whenever we're on site, there's a big, even from authorities, there's a big question about heavy metals and pathogens in the fish, particularly in the fish in the grow-out stages. So this will be a very key focus when we're doing experiments and tests later on. If I go to the next slide. So basically just a brief introduction to RAS. Basically you have a continuous reuse of water. So the water is continuously passed from the culture tanks to the treatment process and then returned back to the culture tanks. The main limiting factor in all of this is the oxygen, which is in this case provided through blowers in the header tank, in the aeration just before the water is returned to the culture tanks. But the treatment process also must control a number of constituents in the water which must be removed before the water is returned back, including solid waste. So we have solid separation, which in this case is being removed by a drum filter, so a drum filtration, and then following this we have a nitrifying biofilter. After the biofilter we have this pumping step. So from the biofilter the water is pumped up into the header tank, and this is the main energy cost in the system. So when we're designing the system, there's a big focus on minimizing the head of the pump required to run the system, because this pump is running 24 hours per day. As explained previously, we're talking about low water exchange rates between 5–10%, and there's this accumulation of dissolved nutrients, of the nitrate, which in this case we are returning back into the MBR for denitrification, but also this water is then going into the agricultural plot. So there's a reuse of nutrients, particularly the nitrogen, the nitrate, and the phosphorus. In the next picture here, this is a work in progress. So we'll finish the installation in the coming months. On the left side, on the left picture, you could see the broodstock system, and in the right picture, you could see the nursery. So these two systems are currently being built. As regards tanks, we try to use a variety of different tanks, since the purpose of this is to demonstrate and for people to learn about the design of RAS systems and mission of RAS. The idea was to use as much as possible local materials. On the left hand side, we designed and built fiberglass tanks, which, although these were built at our facilities and shipped over, there's something which can also be built but as the cost of tanks go, this can't compare to the cost of of standard plastic tanks, as can be seen in the nursery. So we try to include tanks which are locally available and available at a good price. Yes, what else? And then just 2 slides about the monitoring system. So this is something, the monitoring system is measuring in the RAS system. Of interest is the dissolved oxygen in the tank and the temperature and pH in the biofilter. So as monitoring and control goes within the RAS, we're looking at the normal dissolved oxygen, temperature, pH, which are essential in controlling and operating the RAS system. But the monitoring system is also used in the monitoring and control of the wastewater treatment system and also the energy system. So it is a bit over designed in the sense is quite there's a lot of equipment included in the monitoring and control system, because as part of the project we wanted to monitor everything remotely and then decide on what is the most important for such a system, which comes at a later package in the project. So over here, the monitoring and control system basically can log, and you can view all the sensor data on individual units within the RAS system or within the water treatment system, but also it can be also viewed on the main computer, which, if connected to the internet, can be remotely viewed and controlled. This is all done by the partner from Denmark called Oxygard. And in the second slide, basically, you could see on the left-hand picture, you could see this is the interface, which shows the dissolved oxygen and temperature per tank in the system, and the water levels and pH within the biofiltration system. This is all connected to alarms, so whenever there's a certain limit which goes above or below a set limit, there are visual alarms, and which can also come on your mobile phone. And also importantly, if in the RAS system, if the dissolved oxygen within a certain tank goes below a certain level, we have emergency oxygen dosing. So pure oxygen will be dosed directly to the tanks if the DO if the dissolved oxygen drops below a certain level. And this is important in case of extended power cuts. So in case of a very long power cut and there's no electricity, although we have the renewable backup, we also have another backup, which is the emergency dosing of oxygen. All this is automatically done. So I pass the floor to Jan.
Okay, thank you, Julian. Yeah, now I'm coming to our renewable energy concept. As mentioned before, there are actually 2 systems. One is based on PV, photovoltaics. One is on biogas. And we have designed a 15 kilowatt peak system to provide a high or majority of the energy, and a battery capacity to run the system also during night and during power outages of 30 kilowatt hours. And as mentioned, to supply all energy to critical consumers as an aeration system. In addition, we also have a compressed oxygen system if all power fails, so that we are able to keep all the fish and the MBR alive. So this is very important. We have a multi-step system. As far as biogas is concerned, we provide the biomass to the biogas. The biogas system, as you could see at the bottom, this is supplied based on local experience of our partner JKUAT in Nairobi, the Agriculture University in Nairobi. They have for many years experience with this system, as you could see on the left hand, a conventional biogas digester, and we are planning to feed the surplus sludge of the MBR, of course. This is not enough, and we want to blend it, mix it with cow dung, which is can be provided by the neighboring agriculture activities and on the pilot. So since the area near the Victoria Lake is very much still agriculture based, so we are expecting getting enough feed for the biogas generator, and the contribution of the biogas is, as you could see on the right hand, on the very right, it's passed through a generator, a biogas motor, and this provides something like 3 to 5 kilowatt power, so it's rather low. And later you can see that we want to, this is our innovation, improve the systems, enhance the efficiency of the systems of the PV and of the biogas as well. So I can move on to the next slide, which is the novel technology we want to involve in the project. It's called thermoelectric generator. So what is a thermoelectric generator, TEG? It's to be honest, a rather old technology. It was mainly used in space, for space to supply energy in space to the satellites and so on. And what is new is now the technology, the price or the cost of these systems dropped significantly. And now it's going to be interesting also to be applied in environments like in Africa, Europe, and so on. What is the basic principle, without giving you giving any too much details? You need just a hot site and a cool site, and this temperature difference, it's called the Seebeck effect. Probably you have heard about this. It's a physical effect, rather old effect. And you need just a block of material. You need to heat one side, you have to cool the other side, and this is giving you a current or electrical energy. And so the efficiencies are still low. However, the good thing, the very benefit of this system is you have no moving parts. It's very simple. And if you had the material to run it for many years, 10 years, 15 years without any changes, and you can just harvest the energy in a very simple manner. And you can also for sure calculate your operating cost, invest cost, and this is what we want to do in this project to see in future, does it make sense to involve this technology. At the bottom, you could see some of our basic experiments at our university, findings from a master thesis. So when you go up with the temperature, you can enhance the energy from starting from 50 to 200. So we can move up. This is a rather small system, almost 50 watt energy. So the next slide shows you the our combined system. So on the left hand, this is the improvement of the PV panels. So we combine. This is provided by a patented solution from our German partners. The combined PV with the TEG, as you may know. The drawback of all PV panels is that there will be a significant reduction in efficiency by heating. So the higher the temperature of the PV panel, the lower the efficiency of the electrical efficiency. And so it's wise to cool the panels in order to increase this. And this will be done, number one, by the TEG. So the TEG will be fixed with a hot side to the PV. And there will be also a cool side at the bottom, so that one of the effects of the TEG model is to cool the system, and the TEG is also able to harvest some energy. So, and one of the ideas is to create some, and we're going to test this on ground in our pilot activities next, to set up swimming PV panels. So a cooling fin, which is also able to float on the surface of the water. so cooling the system and to have the PV panel on top, and so to harvest energy just not only by PV, however also by TEG. We're expecting something like 10 to 15% higher energy harvesting. So we'll see. Of course, the challenge is always with the cost. Is it cost effective? But we'll see. So we are doing a research project and want to study this. So on the right hand, you could see our second option. We want to combine this TEG on a higher temperature level with the biogas generator, the gas motor. So the hot exhaust gas of the biogas motor will be passed through TEG unit, and is provided by a Italian company. Our pilot is also rather small, so in order to show to give a first step. So the energies, as I said, for the biogas motor is in the range of 3-4 kilowatt peak, and considering the fact that the TG gives you a efficiency of 5 to 10%, we are in the range of 300 watt provided by the TEG. This is our pilot setup, and we want to test. This is unique, so for the first time, and in the African environment, so it's rather new, and we would like to see how it develops. So you see a low temperature unit. This is a PV panel, probably 60 to 70 degrees, and a high temperature unit up to 300 degrees Celsius. So this is our novel pilot testing, and the majority again of the energy on the pilot plant in Kisumu will be provided by conventional PV panels. So the testing is just done by a small part, and it's not contributing very much to the system. So this 15 kilowatt peak is basically provided by conventional PV panels, which are also available in Africa and everywhere. So, and which is now looks like a very, very economic solution due to the price drop during the last 5 to 10 years. Okay, so coming again. So just to recall what I was starting with. Now we have looked into the RAS system explained by Julian. We had some remarks on the MBR with the novel membranes. We have the renewable energy mentioned and explained also by Julian, how the online, or the basics of the online monitoring system. So it's just to recall, to summarize all this, or the technical concept. And this is an image showing you, this has been by Julian's group, and this is a animation. What it basically looks like. On the right hand, you can see the tunnels with all these RAS systems, the hatchery, and there is a small building with an MBR inside and some tanks outside, and we have also a small office for part of the office is used for monitoring some chemical parameters, water parameters, and so I can move on to the give you some details on the pilot site. So we selected a site near Kisumu, near Landa, peri-urban area, and we set up the system next to a waste pond. So this is actually the wastewater, treatment system, or one of these in Kisumu. And the good thing is we can directly tap the domestic wastewater. It's marked as wastewater intake, so we have the ability to take in wastewater. And the pilot is on the left side. So we decided this with the ministry and with the owners of the ground. And what we cannot, initially we thought also to involve fish factory wastewater. However, the fish factories are farther away. So, and we will study this in the later phase. So at the moment we are focusing just on domestic wastewater and near this pond. if needed, we could also take the already pre-treated water. So what we want to start with is with the real domestic wastewater entering the pond, but we could also use water from the maturation pond or from any other stage to feed in. So we have a great flexibility. So there's plenty of water available at different quality levels. And the drain of this wastewater treatment plant goes directly into the lake. So this is one of the very popular technology in Africa, ways to use waste ponds like this. Okay, what are the impacts? In summary, as mentioned, an effective sanitation, wastewater treatment by MBR. This is one of the highlights. Freshwater availability to avoid release of fertilizer. Antibiotics, this will be also studied, of course. There are many details, on water quality. What we have to look at is heavy metals, it's antibiotics, COD level, N balance, and all this will be monitored throughout our pilot period. Use of renewable energies. How can we design a future system? What makes sense? Conventional PV, does it make sense to use the improved PV system with the TEGs? How about footprint? This is something on the life cycle assessment as well, and sustainability studies will be carried out in parallel. Very, very important to see what is sustainable in future in this particular environment. And extraction use of natural products, the agricultural waste, which is used for the biogas production. And of course, very important to see how this fish production, how it could contribute to the fish production in general in the Lake Victoria area. So remember, we are just providing fingerlings, the small fish, and very important in a next step to see how these fingerlings can be sold to the already ongoing aquaculture activities nearby, how the people like the quality. Fingerling is sometimes a bit critical, and people are a bit scared about quality, and we have to show that we can provide good quality with our system so that they can grow big fish and they can have an additional benefit of this. Okay, in particular, the socioeconomic aspects are also very, very important to raise the awareness on environmental production. The technology, as you have seen, there are many elements. So it's like an integrated system. Energy, water nexus, very important. And this calls for training and for guiding the people down there. And of course, number one is to create new jobs. So the job to balance the loss of jobs in fisheries in recent years, to create new jobs so that the people have a future nearby, and to create also business competence in this area. Okay, now I can pass the floor to Julian. This is a bit more on the potential markets. He's more like expert in this. Julian?
Yeah. So yes, as you all know, or I'm not sure, in Africa, fish is a big market for fish. So the demand for freshwater fish is there. Other than the tilapia, there are many other freshwater species which are available on the market and which are consumed. So African catfish, silverfish, Nile perch, lungfish. These are fish which are commonly found on the market and which there's a market for. For as regards the price of tilapia, this very much depends on the size of the fish, and these are prices which we found there on the ground. Two important points, these last 2 points we found are important, is the lack of the cold chain in local production. So the facilities for transportation and the cold chain is sometimes lacking in these areas, and something which could be a market opportunity for bringing the production of the fish closer to the market. And also, obviously, looking at, there's a big demand for fish, as you can see from the large volume of frozen tilapia which comes from China. And then, when we're speaking about urban aquaculture, there are a number of requirements. So producing market-sized fish close to the markets requires setting specific needs. Particularly water, so the need for clean water, the availability of clean water, as well as the availability of space to treat the effluent. Either treat the effluent or connect this to agriculture or ponds or extensive aquaculture. And the other, as mentioned before, the other good thing about urban aquaculture could be the idea of selling fish directly to the consumer without the need of middlemen, although and then the use of RAS for hatcheries. So other than urban aquaculture, the other good market for RAS would be for hatcheries. So the availability to produce high quality fingerlings in this controlled environment. So to produce monosex population, and to be able to supply small-scale ponds and cage farmers in the vicinity. This is something which we hear over and over again, the availability of good quality fingerlings, and other than this is the good quality feeds. In the next 2 slides, what we tried to do is get an idea of a business case. This is related to the VicInAqua project, but the main numbers are related to the hatchery facility. It's important to see that this is a demonstration facility, and it is, as scale-wise goes, it's on a relatively small scale. So as things are scaled up, which will be looked at in more detail later on in the project, and the economies of scale should bring down the cost of the investment cost. So over here we're looking at investment. This 53,000 is a number related to the aquaculture system. So for the housing, for the RAS, for the hatchery, and not including the wastewater treatment system or the energy or other components in the VicInAqua project. And so this is looking at just the aquaculture component. So this slide basically details the main costs in the production of the fish. So looking at the feed, looking at the electricity, particularly the electricity, because electricity is the largest cost component in the running of the facility, the water, and then the labor. So when we're talking about water, if there wasn't the NBR, so in this case we're taking wastewater and using this water in the RAS system. But if there wasn't this source of water, you'd need a municipal supply or a surface water supply or rainwater or a borehole for use of groundwater. As regards labor, for the system, we're looking at having one technician. So one technician will run the facility, or one technician and an assistant, and importantly, a security guard. And the next slide basically breaks down these costs. So looking at the feed per month, the cost of feed for fingerlings, so for broodstock, for the fingerlings, for personnel, so there's a good cost in personnel. But as you could see here, the large cost here is looking at the electricity. And this is assuming it is completely supplied from the grid. In this case, we have the luxury of having it from other alternative renewable sources. But the business case of the combined technologies together is something which we are still looking into. So then there's the cost of water if we use municipal water, and other costs related to chemicals for cleaning, repairs, servicing, and spare parts. And so basically here you have total monthly costs with using electricity and water from the grid, or if water and electricity comes from the remainder of the VicInAqua system. So as a monthly profit, this does not include obviously the investment costs. So this is something which needs to be worked on further. Okay, and I'll pass on the word back to Jan.
Okay, thank you, Julian. Okay, so in summary, what are the key learnings of this webinar? In summary, quality fingerlings, very relevant, very important, as Julian mentioned, and therefore we address this with our VicInAqua project. The bigger fish can be grown in other environment, in other ponds, so probably RAS system doesn't make much sense for the big fish. So therefore we are addressing the fingerlings, the high quality fingerlings, as already mentioned. It's of high political interest. There are many, publications by government to address the aquaculture, try to enhance aquaculture activities for the food, for the market, for the local people, for business, and there are many, as you can imagine, good arguments to foster this. So we need to involve key players, and we are just about to involve them by our partners who are willing to scale up our technology, to launch business on this already mentioned. So the version 2.0 with the lessons learned from our project, very, very important. This is, as Julian mentioned, at the moment, we use the pilot, and all the costs of the pilot are rather high in the project. Why? Because we want to get as much information as we could get by monitoring, for instance. But finally, of course, the marketable size of the technology should definitely look different. Should be simpler, should be less in cost. So this is the thing that therefore we are doing this. We can just give an estimate on future business and all these costs and profits involved. Okay, challenges of course in the environment, the culture differences. But we have learned a lot from our African partners, and they probably also learned a lot from us. So we have a very good team, and so I think we have highly now hired 2 person running the system, highly motivated and working very hard. And of course, training we already started. So ABT gave already training in Tanzania, and we will continue this. We gave energy training in Kenya, and more is coming within the next 6 months. And yeah, as I said, financial sustainability, this is the real robustness and financial sustainability we have to work on. And so for sure we'll get more experience within the pilot phase. And reliable energy supply. So we will also study how about the energy safety. We are connected, as I mentioned, still connected to the net, to the grid, and we'll see how frequent there will be power outages and how we can bridge it. And the power study throughout our pilot action, very, very important. How much can be contributed by the PV system? How much we had to store, and we'll see. And all this data will be collected and mined later on. Okay, so thank you very much. I give the last words to Karsten.
Yeah, so thank you very much for the presentations and giving us an overview for of the project and talking about the technologies and the overall approach. I think it's a very, very nice project which addresses quite a lot of challenges. And now I want to start the Q&A session. Like one question which was raised here, it's about the lifetime of the membranes. And I want to another aspect to this, because this is also something we got asked quite frequently, is what's the lifetime of the membranes, but also can they be cleaned or do they need to be replaced over and over again?
Very important question, because the membranes contribute most to the capital cost. So you know, this is the centerpiece or the heart of the MBR and membranes. And the rest is quite simple. It's just nothing but a tank with an activated, you know, with these bacterial strains, and the rest is very, very simple. And therefore, it's required to have a very long lifespan for years. So based on the previous experiences in sewage treatment plants, the lifespan of these membranes is 5 years plus X. So as you could see, as long as possible for many, many years. Because replacement is very costly. Give you just a figure: 1 square meter of MBR membrane is probably like 40 to 50 euro, and you're able to run this at probably just a house number 20 liter square meter hour. So you could see this is really a cost driver, and frequently need to be replaced as low as possible, so we want to keep them for years. What is in our project, what we expected is that we can, regarding cleaning, this is also an important issue and a cost driver. So our vision is to have a self-cleaning membrane. So we're developing coating which hopefully needs almost no chemical cleaning, but we'll see. At the moment, cleaning frequency depends very much on the water quality. So for the domestic wastewater, it's rather less, probably every 3, 4, 5, 6 months. And for industrial wastewater, frequency may be much, much, much shorter. So, but this is one of the tasks we have to look into throughout the pilot phase.
Okay, thank you. Then I want to add another question which comes from the participants is, and this is maybe it's a question to you, Julian. How does the monitoring system will be replicated to the local reality? Will the local people manage to have similar systems?
That's a good question. The reality is that the system, as is designed in the VicInAqua system, is elaborate. What like a product coming out of this project is a system which is low cost in the sense that it will be just monitoring the parameters which you ultimately require. So if it is aquaculture, what you're really interested in is the dissolved oxygen in the tanks, maybe the temperature and the pH in the system, and whether the pump is running or not. And the idea of what the work they're doing at the moment is to have a system which is completely mobile based. So you have probes in your tanks and an application on your mobile phone, which will bring down the cost significantly. So although the system and the pilot is costly, the idea is to have the objective from this project is to develop something which will ultimately have a lower cost and would be more accessible to the local context, to the African context. So now, how low can the price be is the next question you should ask. But this I don't have an answer to. So this is something which you will have to look at deliverables later on in the project, further down the line, towards the end of the project.
Thank you, Julian. You also just mentioned a very, very important part of the project. The project is also about learning all these lessons. How does a system need to look like that it can be, for example, downsized to the local environment, and learning process for us to get all the information. What is, for example, a price that is affordable? What are the requirements, the local requirement needs, the local environment needs. And
as we're building projects and people visit the pilot facilities, what we're seeing is that people have ideas. So the idea of the project is for people to get ideas, to build a system locally. So a lot of the idea of the system is to be able to have a system which is completely locally built. So quite a number of entrepreneurs and people who work in the wastewater business and aquaculture business particularly, when we're on site, visit the facility and come and think, how could I make this locally? How could I make this for a lower cost? So the idea of the project is to drive this thinking and this learning process.
Yes, and we just mentioned it. We were just talking about a lot about the local requirements. And there's another question we got asked quite frequently is, what is the local opinion on the project? And Julian, you already mentioned that there's a lot of political interest in this, but it's a general question. How do the local people react to the project? What would you say?
Yeah, this is as Julian mentioned. This is one of our tasks to in the next phase, in the pilot phase, to show people around and to explain and to see, to train, and to get the feedback. This is very, very important, to get feedback on the technology. So these people down there, they are very smart. They know very well what they want and how you could do business, the local people. And so we need their feedback and to see also I learned from other international projects, it's always wise to have the local people also regarding cost. What could be accepted? When you come up with some costs, I know it's no go, it's too much. So try to bring it down, of course, the lower the better. But then you can get a very, very good feeling for this, what might be accepted. Also on technology level and from the economic. Yes.
Thank you. Now I want to get to more the technological part of the project, because there was another question raised by you. Is do you also use bioelements in the MBR tank?
So the MBR tank is just like a common MBR, so submerged membranes, flat membranes, that's what we are going to use, and the activated sludge, so the MLSS, so no extra elements. So in addition, we have also a kind of filter. So Julian, you could give some remarks on this in the RAS system. In addition, so but the MBR is nothing else but a conventional submerged MBR tank, like it's running in hundreds and thousands in other sectors, industrial and in the community level. So yeah.
We do in the contrary to the MBR, where the biomass is in suspension, in the nitrifying bioreactors in the RAS, yes, we use a MBBR. So we have biomedia, which is kept in suspension using the aeration in the tank. So it's a aerated tank, and you have biomedia on which the bacteria attach themselves to and grow. So we do use, I suspect what you're referring to, bioelements. So it's biomedia in the nitrifying bioreactor in the RAS systems.
Thank you. I just want to give you a couple of minutes to ask your questions. And one question that's also asked quite often is, because the system is quite complex, what is what are the requirements to run the system? Can it be run by one person? Is it designed to be run by, how many people would you need to run the system?
Yeah, it's a very good question. So we are still learning. We still see how at the moment we have hired two technicians who provide and support the system. However, again, we are in the pilot phase. This means we need more personnel in order to collect as many information as we can get, in order to, just one example, to see the effect of the efficiency of the MBR. You have to measure the COD inlet, outlet, and probably twice a week, and you have to follow all this. When we had collected enough experience in a rather more business-like unit, you do not need this anymore. And we are expecting to run the system with one person in long term. So yeah, and we have many different elements. As you have noticed, we have the PV plus TEG, we have the biogas, and probably or finally we come to the conclusion that for the market it makes sense. I'm just speculating, to run the system just with a PV. With a PV unit. Biogas probably is too, I don't know, too complicated or not viable. So could be also it also depends on the location, or the particular location. Other location, you probably come to the conclusion that it may make sense to run it more like with biogas and PV. But PV in Africa is always a benefit because it's rich in sun, and so the cost is dropping. And but again, this is one of our tasks we have to work on, how finally the system may look like. At the moment, it's a research project, and it's more complex, definitely. We need more personnel to run it.
Thank you. And maybe another question, I think, which is one of the most asked questions we get, is what's the level of autonomy of the system with regard to energy and water supply, for example, and what's the vision to achieve throughout this research project?
Yeah, and the autonomy in energy is we designed 20% plus. So we'll see how far we can get. It's definitely not 100% autonomous system. However, we learned it's not required in Africa, because everywhere you have where you may set up the system, like at the pond, at this waste pond where we do it, and other potential locations, you usually have grid access. The thing is, as I mentioned, how frequent do you have? Do you suffer from the power outages, power break, and of course, how is the system, the economic situation? So what we learned is this is probably coming in the next year. You may also in future feed some extra energy. If you had a PV unit, you could feed it to the grid and you get it reimbursed by the government. At the moment, we studied this. The situation is in Kenya. Like you could do this. You could feed some energy also back into the grid. However, you need to fix the amount, and so therefore we decided not to go for this, since we want to keep our flexibility. So if we had promised to or committed to feed a certain amount, we would lose our flexibility. This could be also, you see, the economic situation and the technical situation. This is needs to be studied. Regarding water, so we are more independent, since what is though the RAS system, the loss, what we need to replace is just the loss of the RAS system, and this will be done by the MBR treated water. So we can tap. We are very flexible. We can tap wastewater. We could for sure feed groundwater. This is the idea. Industrial wastewater treated by MBR. So we are more or less not completely independent, because we have some water, but we are very flexible in this manner. And cost-wise, which needs to be studied about the cost of the MBR versus the cost of tap water. This also depends very much on the location. So this is also an issue we need to study further.
Okay, thank you very much. I think in general, it shows that the project is yeah, quite complex, and I think I just want to come up with it's not a question, it's a comment, but I think it's a nice way to wrap also the webinar, to wrap it up, and this refers to see what the communities will be doing. So maybe we can also give a short vision about the future of the project, maybe also about the future of the pilot, what the vision of the project is regarding what will happen with the pilot after the EU funding or the EU project is finished. Yeah,
they're very, very important. So, you know, many previous projects, development projects ended with the project phase, and after people went away back to Europe or wherever, the project stops. We, of course, are aware of this, and therefore our planning is that so the project will be ending by mid of next year. So we will be starting with a pilot phase after inauguration in November, and then we agreed that the pilot, after the official end of the project, will be handed over to the Ministry of Fisheries and Agriculture in Kisumu, and they will be taking care. They will provide personnel, and they will taking care to run this. And by then, hopefully, we will find a way to keep it running in an economic way. So this means by selling the fingerlings, the cost hopefully could be covered, so as we expected, and to have this as a demo unit, as a demonstration unit to keep for in future interested people who may set up business in this field, that we can always have, like also a training location, a kind of testing location where we can test new technologies, new ideas, as a kind of sample for replication. So this is the idea in long term, and responsibilities will be with the Minister of Agriculture and Fisheries in Kisumu.
Okay, thank you very much, Jan. Thank you very much, Julian, for giving all this or sharing all this information with us. And I think this is also a nice way to end the webinar. And first of all, of course, also thank you for participating in the webinar and having the interest for our project. And I just want to come back what I was talking about at the beginning. If you have any question, please feel free to ask us. We have a website. Just go there, send us an email, or use the contact form to contact us. Also, please feel free to, as I said before, to join our stakeholder community, to follow us on social media, to get in touch with us. I think it's a nice project, and the project also needs these inputs and also needs the exchange with other ideas and people to thrive. So yeah, then we are at the end of our webinar. Again, thank you very much for participating and for all your inputs, and we are hoping to hearing from you, and that you will join us at an event, or we will meet each other somewhere at a conference. So thank you, Julian. Thank you, Jan.
Thank you very much from my side as well.